Hello everyone. In today's lecture, we are going to understand one of the most fundamental semiconductor device used in electrical and electronic engineering, the PN junction diode. You may have seen a diode in a rectifier, rectifier circuit, or in the power supply, or in the power supply voltage regulator, voltage regulator, then the protection circuit, protection circuit, switching circuit, switching switching circuit, and many more electrical and electronic systems. But the important question, why does the diode allow current to flow mainly in one direction? And what happens inside the semiconductor when voltage is applied? If we apply the voltage, then what will happen? Then what is the depletion region? What is depletion region? What is potential barrier? Potential barrier. What is potential barrier? And what exactly happens in the forward bias and reverse bias condition? In the forward bias and reverse bias condition. Reverse bias condition. So in this video, we'll understand the complete working of PN junction diode from the formation of the junction to forward conduction, reverse blocking, and breakdown. So let's start. First, we'll see what is diode. What is diode? What is diode? So a diode is a two-terminal semiconductor device. The two terminals are anode and cathode. So we can write here that anode and cathode. These are the two terminal. The diode is normally made by forming a PN junction between a p-type semiconductor and n-type semiconductor. The p-type is associated with the anode, p-type is associated with the anode, and n-type is associated with the cathode in a conventional PN junction diode. Now, the most important property of the diode is it conducts current easily in one direction and strongly oppose the current in the opposite direction. It will conduct current in one direction, but it will oppose the current in opposite direction. So this property makes the diode extremely useful in electrical and electronic circuit. Used in electrical and electronic circuit. Okay, but to understand this behavior, we need to understand what happens when the PN and N material are joined together. When these two P material and N materials are joined together. Okay, first now we'll see the formation of PN junction. So when this p-type semiconductor, in a p-type semiconductor, holes are the majority charge carriers. These holes are the majority charge carriers. So a hole represents the absence of an electron and behaves as a positive charge carrier. So these are behaves as a positive charge carriers. So therefore, p-type, in case of that p-type, holes are the majority carrier. In p-type, holes are the majority carrier. Holes are the majority carrier. And in case of a n-type, so in case of this n-type, the electrons are the majority carriers. So here the electrons, so these are the negative charge. These are all are negative charge, and these are the electrons. So electron is the majority charge carrier. So in n-type electrons are the majority carriers. Now, if we joined these two material together, then it will create a PN junction. And this PN junction, is responsible for the unique behavior of the diode. Next, we'll see the formation of depletion layer. So as soon as the p-type and n-type materials are joined, This p-type and n-type materials are joined together, so there is a difference in the carrier concentration. So n side contains large number of electrons, so this contains large number of electrons, and p side contains large number of holes, large number of holes. So therefore, due to the concentration difference, electron starts diffusing from the n sides towards the p side. So electron starts diffusing from this n side to the p side, and similarly that holes are starts diffusing from p sides to the n side, p side to the n side. Now near the junction, what will happen? These holes and electrons are meet each other and recombine, near the junction. As a result of this recombination, free charge carrier disappear from the region around the junction. So this region is called depletion region. This region is called depletion region. This is the depletion region. This region is called depletion region, and it is called depletion region. Depletion region because it depleted depleted of mobile charge carriers. Charge carriers. Charge carriers. Okay, this is the depletion regions. Now we'll see the formation of the potential barrier. So potential barrier and electric field. But okay, potential barrier and electric field. Now, so when it is when these two layer is joined together, then the electron is diffused from that n side to p side, and holes are diffused from the p side to n side. Now, when the electrons leave the n side, when these electrons leave the n side near the junction, they leave behind the positive charge donor ions. They leave positive charge donor ions. Similarly, when holes leave the p side near the junction, negatively charged acceptor ions remain behind. These are the negatively charged acceptor remains behind. So therefore, fixed positive and negative charges are created around the junction. As this is the junction, so these are the fixed positive and negative charge is created. So these charges establish an electric field across the depletion layer. So it's create an electric field across the depletion region, and these electric field oppose further diffusion of majority carriers. So this just it will oppose further diffusion of majority carriers. So as a result, a potential difference develops across the depletion region. So that it will create a potential difference. So this is known as the potential barrier or barrier potential. This is known as potential barrier or barrier potential. Barrier potential. Barrier potential. So for a typical silicon PN junction, the barrier potential is approximately 0.7 volt, and for a germanium it is 0.3 volt. So remember, first is diffusion of carriers, then recombine recombine recombine. After that, there is a depletion region, then electric field, then potential barrier, potential barrier, potential barrier. So this is the basic formation of the PN junction diode. So this is the basic formation of PN junction diode. PN junction diode. Okay, now we'll see if what happens when the external voltage is applied across this diode junction in equilibrium position, unbiased PN junction. Now let's consider a diode with an external voltage source. So this condition is called unbiased condition. So inside the junction, the two opposing inside the junction, two opposing processes exist. The first is diffusion. First is diffusion. First is diffusion. Majority carrier tend to move because of the concentration difference. And the second is drift. Second is drift. Drift. So the electric field in the depletion region produces a force on the charge carrier. So at equilibrium, these two effects balance each other. This is the diffusion, another one is the drift. So, and at equilibrium, these two effects balance each other. So therefore, no net external current through the diode. No net external current is zero in this condition. The depletion region remains established at this junction. So because of that this depletion region remains established at this junction. This is called unbiased condition. This is the unbiased condition of the diode. Now in next we'll see the forward bias condition. In case of that forward bias condition, what will happen? So in a forward bias or forward conduction mode, so now let's connect an external battery similarly like as previous one. Suppose when we connect a external battery with this diode, so this is the P, this is the N, this is the anode, this is the cathode. If we connect an external battery with this diode, that positive terminal of that battery is connected with the P side. This is the positive, it is connected with the P, and this negative terminal is connected with the N side. N side. So this is called forward bias. This is called forward bias. Forward bias. Forward bias. Now let's see what happened inside the diode. So after one external field oppose the junction barrier. So whenever we are connecting a source in this position, or where this positive terminal of that battery is connected to the P and negative terminal connected with the N, so it will create an external field to oppose this junction barrier. This junction barrier. So how it is creating? So the electric field produced by the external voltage acts opposite to the built-in electric field in the PN junction. So whenever it is positive, this is also positive, this is negative, this is also positive. So this is negative. So what will happen? So these positive charges, and here also these are positive. So these both the positive will repel each other. So that's why it will create a force in this direction. And this is also negative, this is also negative. So because of that, it will create another force in that direction. So these force create an create external field to oppose the junction barrier, this barrier. So therefore the effect of potential barrier decrease, and the depletion region becomes narrow. Depletion region becomes narrower. That depletion regions become, because the barrier is reduced, the depletion regions becomes thinner. The majority carriers can now approach the junction more easily. Now when it is narrow or thin, that depletion regions, so in that case that majority carrier can now approach the junction more easily. The majority carrier cross the junction. So electrons from the N sides receive sufficient energy to cross the junction towards the P side. This cross the junction in the P side, and at the same time holes moves from the P sides towards the N side. So therefore substantial carrier movements occurs across the junction. So then the substantial movement occurs across the junction. Then a large current large current will flow. Large current will flows. So once the applied voltage becomes sufficiently high, this applied voltage is sufficiently high, so at that time the diode conducts a significant forward current. So for a silicon diode, the commonly used approximate forward voltage is around 0.7 volt. For silicon, it is 0.7 volt, and for germanium, it is 0.3 volt. So however, remember that these are practical approximate values, not absolute switching points. The actual diode's currents depends continuously on voltage, temperature, and the specific diode characteristics. Now, reverse bias and reverse blocking. So let's reverse the battery connection. So here we have connected this battery in the reverse bias condition. So in this condition, that positive terminal is connected to the N side, This positive terminal is connected to the N side, and this negative terminal is connected to the P side. So this is called reverse bias. Now the behavior of the diode change completely. Means the external electric field now supports the electric field already present in the depletion region. Already present in the depletion region. So that because of that, these depletion regions becomes wider. So this will now widen. So because of this wider, it's because of this region becomes wider. The barrier opposing the majority carrier movements, it's became stronger. Now, these majority carriers cannot easily cross the junction. This cannot easily cross the junction. So, very small current will flow. So, although the diode blocks that majority carriers conduction, a very small current exists, and this is called a reverse saturation current. This is called reverse saturation current or leakage current or leakage current. So the current is mainly associated with the minority carrier. So therefore, in reverse bias, large current does not normally flow. Large current will not flow. So the diode now behaves approximately like an open switch. Now it will just approximately behaves like a open switch. Now we'll see what happens if the reverse voltage becomes very high. Reverse voltage reverse voltage becomes very high, very high. So in this condition, what will happen? So now imagine that we continue increasing the reverse voltage. So if we continue increase this reverse voltage, then what will happen at a particular voltage? The diode enters a region called breakdown region. So it will this reverse current will flow, and this is the breakdown regions. This region is called the breakdown region. So the reverse current suddenly increase. So here this reverse current suddenly increase. There are two important mechanisms associated with this breakdown. And one is Zener breakdown. One is Zener breakdown. Zener breakdown. So Zener breakdown generally occurs in heavily doped junction. It is occur at heavily heavily doped junction. Heavily doped junction. So at relatively low breakdown voltages. Another one is the avalanche breakdown. Avalanche breakdown. Breakdown. So in this avalanche breakdown occurs when the charge carriers gain enough energy from that electric field and produce additional electron hole pairs through collisions. So these cause a rapid increase in reverse current. So what because of this rapid increase in reverse current, rapid increase in reverse current. So importantly, ordinary diodes can be damaged if excessive breakdown current flows allowed to flow. So specially designed Zener diodes are intended to operate in breakdown for voltage regulation applications. So mainly this breakdown is withstand by the Zener diodes. Zener diode. So mainly this Zener diode works in the reverse bias condition, reverse bias condition. Now a diode as an electrical switch. So we can now understand why diode is often compared with a switch. So during the forward bias, during this forward bias, the diode is on, current flows. When the diode is on, current flows, and during the reverse bias, this diode is off, so no current will flow. So of course a real diode is not an ideal switch. So it has forward voltage, then the leakage current, dynamic resistance, then the switching time, and the other non ideal characteristics. So from this equivalent circuit and the symbol representation, when it is in on state, so at that time it will act as a short circuit. So switch is switched on. So in this circuit, what you can say, when it is in off state, it's non-conducting. So at that time it will work as an open circuit. So diode acts like a one-way bulb for electricity. It allows to flow current. Current allows to flow. Cu- Current flows in one direction only. One direction only. So this is all about the diode. Thank you everyone.